we have, and now English is the perfect language for it, because we have two talks that will be in English in the end, and that's two talks about very big topics. We have heard a lot about the practical stuff, how to implement bots, how to bridge the gap between the bot and the customer agent, how to make money out of it, how to sell via WhatsApp, and how to design dialogues. And we'll step one step higher. We'll talk about language now. The really interesting question we will be facing now in the next talk from Hans Uszkoreit is, does the technology need to understand language to really be a good respondent? And that's an interesting question. You would never, as a marketer as I am, you would never come to that idea because you say, of course, that's the way it is. But I think Hans knows a lot more about this topic because he works on that for plenty of years. It's about natural language processing. It was a very big topic, I think somewhere around the 2000s, when response systems started, when we had the dictation systems and software. Then it went a bit quiet, and now since the last couple of years, this is huge. If we talk about automatic translation, if we talk about language processing in systems like GPT-3, and of course, if we talk about bots and dialogue systems. So welcome on stage, Hans Uszkoreit. He is the director of the DFKI.
Hi, good afternoon. I'll be happy to talk in English if preferred, but I could do it as well in German, whatever you like. Should I stay in English?
We would love to hear you in English.
All right, then I'll stay with English. And without more remarks, I'm going directly into my slides and hope you can see them now. The question indeed is, do conversational agents need to know what they are talking about, and how do they do that? How can they know? I start, of course, with an introduction. Then I want to contrast two types of AI systems. You all know them, yeah? It's only to create the awareness for my central question. We'll then talk a little bit about the combination of both worlds in I can show you these things in a more, yeah, maybe that's bigger, right? Combination of both worlds in a powerful chatbot, show one possibility of combining them. Then I will go into one of the latest fads or waves in language processing, large pre-trained language models like GPT-3, and we'll get into the question, how can knowledge be combined with those language models? Because it's pretty clear that they will play a role for chatbots and for conversational AI in general. So I do not have to introduce the basic setup of spoken dialogue systems in this audience or in front of this audience. It's clear what's involved. And the interesting thing then is what happens there in the dialogue management part. And there are two major groups of conversational agents that may have been discussed already. I'm not so much interested in therapeutic or social talk chatbots that do some chit chat and small talk, but I will concentrate on the ones that are more important for business, the ones that are task oriented, that work in call centers or as control systems for smart devices. So things that become useful in certain environments. I will concentrate more on the ones that are in the area of information access or information requests, less on actions, but what I'm going to say actually applies to both. So as we know, there's quite a complexity to conversational assistants or conversational agents. We can differentiate them as to the degree of initiative, whether it's completely system initiative or user or mixed initiative, with respect to medium and modality, with respect to the closeness to true dialogue faculty, to true dialogue capability, starting from simple search, question answering, simple command execution, going all the way to multi-term dialogues. And then what I want to concentrate on is what types of knowledge need to be in the systems or will be in the systems of the future. This talk, although I've also worked in quite a number of companies and work actually now predominantly in a spin-off company of DFKI in the area of natural language understanding. But actually here I'm going a little bit more into the systems of the future. So what will be in store for systems in the years to come now? And with respect to types of knowledge, we know that there are simple systems that have complete answer lists, answer templates. Some systems have access to databases. There are dialogue models. There's now neural conversational system models and language models, which I will address. And yes, there are two very different types of AI systems. They have been with us from the beginning on, and we are aware of them, but sometimes we don't keep them apart that way. So already in the very early days, I worked, for instance, at SRI International in Stanford. We had some robot control system that controlled a robot without any real knowledge. The robot doesn't know how the robot is moving around and moving an arm. Yeah, it is all behavior, but the behavior is not learned. At those times, there was not so much machine learning. It is fully programmed. Yeah, all the movement is in equations, in math. Yeah, and then on the other hand, we had rule-based systems like expert systems for credit check, and they were based on explicit knowledge. The systems based on behavior, they are based on implicit knowledge, just like our knowledge that the knowledge of riding a bicycle we have. Yeah, we don't know how to do it. We cannot explain it, but we can show it. We can do it. We can practice it. The same goes for dancing and for swim. But now guess, what are we doing with language? We think it should be knowledge because you say you know a language. But does the child really know how to use a language? Does the child know what a grammar and a subject and an object and the verb is? And still the child can speak. Actually, because early child language is behavior, not explicit knowledge. So then machine learning came, and systems based on knowledge tried now to acquire the knowledge via machine learning, and systems based on behavior tried to acquire the behavior by machine learning. And it turns out that all the big success stories of so-called narrow AI, machine translation, Tesla autonomous driving, nuanced speech recognition, it's all behavior. None of these systems know what they are doing. A translation system doesn't understand. Google Translate, started by Germans, by the way, does not understand a single sentence. Tesla autonomous driving does not know the traffic rules. And nuanced speech recognition doesn't know about phonemes and about how the pronunciation in southern France differs from northern France. But it can handle language. On the other hand, then there are systems that have explicit knowledge, like IBM Watson knows a lot about medicine, for instance. The Lenovo chatbot, which I will use as an example because I worked in China for several years as chief AI advisor for Lenovo, where I also worked very closely with this chatbot group and was kind of mentoring the chatbot group. And then the DFKI Big Data Text Analytics also has some real knowledge. And that doesn't mean, and now you see two little dots appear here inside the blue, that doesn't mean that they don't use neural networks that just train behavior. No, they mix these two worlds. And this is what the talk will be about, this mix. But before, let me mention, you all know the latest way of storing large amounts of knowledge. They are called knowledge graphs. Everybody knows the word now, Wissensgrafen. Those are semantic networks, in which you have concepts and you describe the concepts by showing the relations they have among each other. And one of the most popular knowledge graphs is the huge knowledge graph of Google. And when you Google something and you Google an entity that has a knowledge graph entry, like a person, or maybe not yourself, but maybe a politician, an artist, then you get an, like here with Leonardo da Vinci, you get an info box. And everything that's in there, and that's why they can use the same knowledge graph in different languages, is that that now Leonardo da Vinci is shown in certain of his properties or his relations to other entities, when he was born and so on, and which the parents were and so on. And these knowledge graphs can be pretty big. So the Google knowledge graph has more than 5 billion entities and 500 billion facts about them. And Wikidata is smaller, but also is quite big. And we are using knowledge graphs in industry, for instance, for storing industrial companies and their products. Here's a small knowledge graph fraction of a takeover. That's kind of a knowledge graph that we extract by understanding texts in newspaper. No, that we don't need here. So when the neural learning, even already with statistical language processing, but when neural systems came in, people tried to do end-to-end dialogue systems. Instead of having all these boxes separate, the interpreter, the generator, the dialogue tracker, they talk about end-to-end dialogue systems that have a single statistical, in fact, a neural model. And this is possible. Many very smart systems work with that way. But in that sense, all the knowledge that's needed would have to be in this model. And we will talk about how it may get there. In general, in the first systems of that time, it didn't get in there so low at all. The people who designed that system, very famous system, mentioned himself, it's not clear whether end-to-end approaches will work with any dialogue domain, and then giving some examples where, like complex negotiations and so on, complex strategies. But the limitations are very easy because these systems cannot deal with dynamic knowledge. By the time this model is trained, all the knowledge needs to be in, but we know from CRM solutions and many other places, knowledge changes all the time. So the problems is not only new knowledge, it's also outdated knowledge. How do I get knowledge out of the system of the It's very, very difficult, because not only that the old knowledge is still in the system, but it is statistically much stronger because it has been mentioned already many, many times, whereas new knowledge is in numbers of mentioning very scarce and has less weight in the neural system. And another problem is that some of the data combinations are very scarce. So if you have many ways of referring to the same machine, to the same product, and some of these ways of referring to it are less frequent. So some of the combinations of words, of entities would be so scarce that even in the largest knowledge models, or in the largest language models, you would not find them. And also, if you know about CRM systems, about customer contact centers, you know that every day there are these changes. People tell them there's a marketing campaign, mention the following thing, or maybe don't advertise this product because we cannot deliver it in large enough numbers. So please mention other things. So there's changes from day to day. And the last point is then the size of the model. If you put in a huge amount of knowledge, it depends, of course, on the size. For Lenovo, Lenovo has now not only computers like the ThinkPad, and lots of laptops, but it has also mobile devices. It has printers, many other types of products, and having the database, I mean, we know how big it is, the database of all these products, for instance, the Motorola phones, Motorola also belongs to Lenovo. It's so big, you can, the language model would have to be blown up again, So So let me then use as an example for mixing the two worlds this conversational agent at Lenovo. I jump over here. It's a conversational agent which has a fallback of call center agents. It can be accessed via web client and WeChat, Facebook apps. It also has a spoken version, yeah, where it can be attached to a phone. And then it uses a knowledge graph, but not only a knowledge graph. I'll come to this in a moment. The challenges are, again, that you get sometimes combinations of chit-chat and facts and instructions, and sometimes troubleshooting. Yeah? Sometimes you don't want any facts, but you want hands-on help by the agent. Yeah? And there are real-world examples. So Molly is the name of this virtual agent, and then has a customer, and it needs to first find out what phone model it has. Here it's the Moto G3 and so on, and then it can answer the question. But where does it look up this stuff? Yeah, and here we come already in a very large product knowledge graph. It is looked up by the dialog manager, and then there is for frequently asked questions and for question templates, yeah, where you do slot filling, this question answer knowledge graphs. I will give two examples that we can jump over. This is part of the product knowledge graph, and there are some things shared by the Moto Z2 and the Moto Z, or Moto Z and Moto Z2 Play. And like the Hasselblad camera and the JBL speaker and so on. And now those are mods, those are add-ons to these that you can attach. I don't know if you know Motorola phones, you can add on other hardware to these phones. And many questions by the customers go about compatibility and how to do it and so on. And then there is also, as I said, the other knowledge graph of answers, yeah, of possible answers, actually question answer pairs, yeah, and which is also used for answering. So I think we can go over here. That's not so interesting. I jump over because otherwise I cannot get. So now the big new thing is these huge language models like GPT-3. I just wanted to, because some of you may ask yourself, are they changing the whole world now in the world of chatbots and conversational systems, or will they not? And the answer is, it depends. It really depends on exactly how my question of my talk is answered, namely how to combine it with explicit knowledge. Because these huge language models don't have any understanding. They work completely without understanding, but they do stunning work in answering questions, really stunning work. How do they get this implicit knowledge? In addition to just having a language model, like having n-grams, a trigram or so, and the probability of one word to follow after two other words, it does lots of pre-training. And the pre-training is done completely without any labeled data. The system labels the data themselves. It generates from the text data because it takes out certain parts of the data of the text, and then the word that's taken out is a label, and then it trains, and the system is supposed to learn which words fill the text. And in doing so, the system learns an immense type of semantics without knowing what it does, yeah? Only implicitly. And then this is combined. G is, by the way, generative. The model can generate. Yeah? The T stands for transformer, and the P for pre-training. Pre-training, I just mentioned, lots of simple tasks, and the model is already trained on some tasks, and later it can be used for text classification, for summarization, or for question answering. So, and the transformer model is something I cannot describe. It would take at least an hour, to describe it. But actually what it learns, the system learns now how things in several layers, it learns how parts in the sentence that are not next to each other, not in the same trigram, not very close to each other, are connected. Yeah, it learns that. Like, schrieb eine lange Passage über die Internetzensur ab. The up is connected to Schrieb, or those parts will be exchanged without charge that got damaged during shipping. That got damaged during shipping, we call it, it's an extra post relative clause. It's at the end of the sentence. It needs to be connected before you can do understanding to those parts. Yeah? Otherwise, you don't know what will be exchanged and so on. So, and if you have these things together, GPT, the generative, pre-trained transformer model, then you can do miraculous things. You can do the pre-training, yeah, and then later you give it maybe in fine-tuning question-answer pairs, like when was Franklin D. Roosevelt born, and then T5 stands for text-to-text transformer, transformer. Yeah, it transfers from text to text with a transformer model. Then it can do question answering. Yeah? So it has pre-training and then fine-tuning, which we may call normal training. And now these systems have become so huge. Yeah? GPT-3 has to become very, very big. It cost many millions actually just to train the system. Yeah, took thousands of machines, and so how can we ever use it? Yeah, and now this is GPT-3. The next generation of these models is so big. Now the red thing down there is GPT-3. Now the switch transformer of Google and the Wudao in the Beijing Academy of AI are already around 9 to 10 times larger, and the next generation is around the corner. So they are huge, but will they change the picture in conversational systems? Yes, in the long run they will. And they have certain strengths in text generation, summarization, summon question answering, translation, event detection, but they also have weaknesses. They cannot solve inference problems. They have no common sense, no natural language understanding. They cannot analyze events, for instance. For some things, they are useless. Yeah? For others, they are very good. So, for instance, they cannot handle the so-called Vinograd schemas. Vinograd came up with that already in 1972. He said, this would be very, very hard for AI, very, very hard. Yeah, things like die Bauern verkauften ihre Kühe, or in English, the farmers sold their cows because they did not yield milk anymore, versus the farmers sold their cows because they needed the money. In one of the sentences, it's the cows that don't give the milk, and the other one, it's the farmers that need the money. And this is something that a GPT-3 cannot understand. Yeah, GPT-3 would not get these things right, would answer maybe the wrong questions. So then people have found ways of now doing. This is a group at Google who built a very smart system that filled in lots of external knowledge into the normal system, but they did it in a very selective way. Whenever there is something which the system would find hard to learn, yeah, for instance, we paid 20 so-and-so at the Buckingham Palace gift shop. Now for putting in pounds as the British currency, it would help you to know that the Buckingham Palace is in, we know that, yeah, but does the dumb system know, is in London, yeah, is in England. And so this system said, oh, we help the learning by using text, by using knowledge. We built a retrieval system. The retrieval helps putting in the right systems, and by putting in what the retrieval finds, it makes very good connections, namely between Buckingham Palace and United Kingdom and so on. So it brings in more connections and knowledge into the language model. So then another group came and said, oh, we can do better. We can bring in all of Wikipedia, of Wikidata knowledge from the knowledge graph of Wikidata, all the 95 billion entity information there, we simply make out of the part of the knowledge graph of these triples. Actually, they are all triples of information that together form the graph. We translate all these micrographs, yeah, like this one here, into sentences, and then these sentences go in as if they had been read. So that means the whole database is turned into language, and then the language is filled in together with all these other billions of sentences. And that way, all the knowledge is in. But if you are careful, you already realize now, wait a minute, how to deal with the dynamic information. No, you cannot, unfortunately. Everything is put in at one stage. And now if there's dynamic information in, too bad, yeah. All the system would have to be retrained if some of that knowledge is overwritten by new knowledge, yeah, which will not take place with a Buckingham Palace, but can easily take with a Moto G3 phone. So there are two ways of dealing with it and keeping the dynamic way in. One would be to apply systems like we have it for relation extraction and then do the database query. Why can you do that? I mean, we applied it already to some chatbot work, but that's not our main goal. It could be done because actually we are not interested in understanding every word in a query or in an input sentence. For instance, this sentence, can you tell me which photo enhancer programs would be suited to run on my new Moto? And already the system asked, if you were paid attention before, which Moto the guy has a Moto 3, actually the G3, then it would now translate into the following query. You check now in a is-a relation, is there an is-a relation between something and the photo enhancer, which one is the photo enhancer, and now a join runs on the Moto 3. And then you get the response, and now you need, of course, to phrase the answer, which is then you could use, for instance, this database of answer templates. That's a possibility. So that's one possibility. There is another possibility, which I claim will be, and we tried it only for entity linking, but it has, I guess it would have quite, it's difficult to do, but it has quite some potential. Namely, if you don't have a frequently answered question, something that you can answer easily, but actually you would need the knowledge. Yeah, it is a factual question. Let the language model generate a query in the knowledge graph. Actually, that's not so difficult, yeah, because these large language models, they can even formulate program code, yeah. I mean, if you know the literature, they do miraculous things if you train them to. So you would generate a query, and then you would do the query, and now you would do the enriched query question. You would ask again with already the lookup, and now the system, the language model, would use this for doing the correct answer. Yeah, so this is, I'm coming to the end now. But let me do, before I come to the conclusion, yeah, let me do a short excursus, detour. Then one of the big new business application areas for conversational AI is in enterprise AI, in business processes. This is more difficult than in customer care, yeah, because the desiderata, the demands and quality accuracy are much higher, and but it is inevitable that this will come. You already see that in big companies that work with enterprise software, enterprise solutions, they are heavily working on it. So that will be a huge field of business in the next years. The participants of any business processes should be able, just like customers, to get information on the state of the process. Yeah, what's the current process? Has it been paid? Has it been shipped? What has taken place? And on the task and rules, because there may be many processes. Maybe the agent, the participant has forgotten a rule. Who can authorize that shipment, who cannot, yeah, and wants to ask a question. It's also for training new members and so on. So such a system would have huge benefits. It would need access to the data of the process and to the entire process model. We are working on that in a different project where we get process models, both in language form and in process model language, and a special process model language, yeah. But these things are so dynamic that feeding them into a language model would be completely impossible, yeah, because it's against the whole spirit, because this changes, yeah, the state of the process changes hourly in a minute. And so the only possibility that we have now, if we want to keep the language models with their huge power, would be to connect these language models with a lookup to the knowledge state, the database or the knowledge graph, because usually also these business processes use knowledge graphs. Okay, I can finish now. Conclusion and outlook. So for high quality flexible tasks-based conversation systems, we need a combination of neural language models and explicit knowledge repositories. There are different ways of combining them that I showed. If we run them in parallel, we may lose the power of natural language generation, because the generative part in the GPT is the generation. It creates wonderful language, much better than other generation models. We would lose it. But if the model could use a knowledge query or lookup, the system would do exactly what human intelligence does. Why? Because this is exactly what human agents do. They answer questions, but they cannot have all the knowledge on all the parts and on all the processes in their head. They look something up, yeah, and then our conversational systems would just behave as intelligently as humans who have an extended memory outside and use it, yeah, consult it whenever it's needed. Okay, let me finish with that. Most of domain-specific knowledge can be built outside the model, has advantages for workflow and security and maintainability. Thank you very much for your attention.
Thanks a lot, Hans Uszkoreit. I have just one question because we're low in time. It comes from another discipline. We try to analyze contents on the web via semantic analysis, and we always struggle with irony, sarcasm, and multi-meaning terms. Multi-meaning terms, I think, is feasible, like you showed us, but how about irony and sarcasm?
Very, very difficult. Very, very. By the way, this is something that if you would do small talk, yeah, in some points, these huge language models, GPT-3 actually was catching certain types of irony and responding appropriately. But this could not be combined with these factual stuff, yeah, with these factual. Hopefully, people use irony only for the small talk part, for the kind of meta talk, meta conversation, or chit chat or small talk. Because if irony is connected with the knowledge part, that's completely different. Because you need to have even more knowledge in order to understand that something is meant ironically. Yeah? So it is nobody would have a solution to that. With other types of irony, surprisingly, a language model can handle. Why? Because it has seen so much irony, yeah? And very few people are so creative to come up with new forms of irony. Yeah? So usually the knowledge system has seen them all. But if you connect the irony with this, so for instance, there's a system that should be smaller from Motorola, and the person would say something like, do you have it in an even bigger size? Yeah, meaning that actually is complaining about that it's too big. Yeah? This is something the system could not catch, yeah, because the system does not know how big things should be in the eyes of the user.
That's what I thought, but I think in the end of a conversation there could be ironic comments about the results that a system gives out, and there's even a philosophical question behind. Maybe at one certain point of time in the future, we as humans try to differentiate us from systems, from computers, from robots by talking differently so they don't understand. It's like our youth does it with us as parents, something like that. But we will never know. Hans, thanks a lot for that talk. It was a very deep knowledge and a bit hard to follow everything of it, but I'll read it after.
All right. Okay. Thank you very much for having me. Thank you.
Thanks a lot.
Bye-bye.